Uh, I'm really glad to be here today. I hope that you enjoyed the talks before. So yeah, let's see my talk, hopefully. Yeah. So today I'm going to talk to you about automatic spend classification, which is a really exciting topic. I will show you an end-to-end solution. We'll show you some technical details and some ideas that helped me through the project. Quickly about me. We have a problem. Yeah, we are back. So quickly about me, I'm Emir Ombasic. I'm a developer more than a decade now. My background is in mathematics. And the past 7 years of my career I spent at Jagger. Now, Jagger is the world's largest independent spend management company. We work with tremendous amount of procurement data on a daily basis, and this project actually leverages some of this data. So before I go into the technical details, let's talk about spend analytics. What is spend analytics? It is essentially a process of classifying and analyzing your spend data in order to make better procurement decisions. So unfortunately, usually in most of the cases, it looks like this. It's really unreliable. As we can see, for example, monitors and printers are put into one category, chairs, cupboards into another one, and unfortunately, we have lots of unclassified articles. Now, this is still a big challenge in the procurement business, one of the biggest ones, actually. The ideal case would be if we would have something like this. So, for example, we can see that the printers are bulked together, the monitors are put to the same category, the cupboard, the chairs, and so on and so on. And when we have a good classification like this, then we can do better spend analytics. Let's talk about the process itself. So usually what it happens is that some member of some company or an employee, he needs something for his everyday business. So let's say this person needs a printer. So what he would do is he would create a query, some textual inquiry, and this inquiry usually goes to the purchaser. Now, purchaser is the guru. He's the guy who knows the market, and he will negotiate with the with the suppliers, and also will try to map this textual inquiry to some catalog or to some number. On the other hand, it's possible that, for example, we have bulk of products or bulk of invoices from the past, and we will try to map them again to some number. And this is the area that we are actually focusing on. So we take the textual representations of these articles, these products, these invoices, and using machine learning techniques, we try to map them to some catalog, and out of that, we get the classification. With the correct machine learning algorithm in place, we can even flip things around. So now, when somebody orders something, let's say a printer, we can directly look it up or predict it with this machine learning neural network, and we can classify it and then send it to the right purchaser. This is good because then we can stream who will order what. If, for example, if we want to order a printer, we predict the category of this printer, then the purchaser who is in charge of buying office supplies will get this inquiry. Now, this solution classifies articles towards this so-called A class. What is an A class? It's essentially a cross-industry classification standard, and it's used as a common language between purchasers and the suppliers. So if you have some product, you will be probably able to map it in one of the categories of this classification standard. It has 4 levels. It contains more than 10,000 categories, and it supports 4 languages. It's an international standard, but it's mostly used in Europe. But for the US market, we have something similar, and it's called UNSPSC. almost the same structure, but different category names. Yeah, so let's see some examples. If we would look, for example, for a laser printer, we could see that in this classification standard, it belongs to this information and communication and media technology, and then sub-level peripheral device, printers, and then laser printers. So the number which represents this category is 4 pairs of numbers, whereby the first pair of numbers is the topmost category, and the second pair the deeper category, and so on. If we would look for an inkjet printer, then we would have also the same 3 categories on the top, and the last one is a bit different. Yeah. So this sounds easy, but now we come to the challenging parts. What if we have some specific product numbers? What if the invoice data contains only these numbers? Then the purchaser cannot know, okay, what is this? The purchaser cannot know every product number by heart. Also, we have some other complex cases, like, for example, if we have typos, or we have plurals or synonyms. And the third and the fourth example actually applies more towards bulk processing of data. Therefore, we developed a machine learning solution, which is written in Python. It's using TensorFlow and Keras. For data processing, we use TensorFlow Extended and Pandas, and we serve it via Flask. So let's look into the data. As I mentioned, we really work with large amounts of data, so I just sampled some portion of it, which still is about 30 million records of products. This data set contains the title, the description, mapped to some A-class. So this was the training data. Of course, I put aside a part of it for testing purposes. Now, what I did on top of that is I cross-referenced it with the existing categories from the A-class. And out of that, I was able to create a database of about 12,000 synonyms of words and plurals. And when I finished that, then actually I built up a vocabulary. This vocabulary contains about 800,000 words, and out of these words I built so-called n-grams, and this I use for typo detection and for typo fixing, of course. Okay, so now finally we come to the neural network. That's where we are here, I guess. If we would look on the internet, like for neural networks for classification, we usually stumble upon some cases like, I don't know, cats or dogs, or the means number classification, like classifying numbers 0 to 9, which has 10 output classes. So people usually tend to solve this issue with one neural network. Now, the ones of you who worked with classification problem, you know that we have usually one layer at the end, which is in charge of telling, okay, what is the prediction? And how it works is that actually it tries to assign a certain probability of every of the possibilities. And this, of course, sum of all probabilities is 1. But in our case, we have 13,000 possibilities, so this was not working really well because the probability distribution was not so good. So of course, one model approach was not working. So I decided, okay, let's do divide and conquer. I was thinking like, okay, maybe I can build 4 different models, whereby every of these 4 models is in charge of predicting one pair of numbers. So the first model would like get the string, the tokenized string, and then it will predict the first category, and then separately we send it to the second model, and this one also will try to predict the second category, so the next level. But the problem here is that the second model is of course not aware of the first one, so it's not context aware. And I did this with the third level, fourth level, and as you can see here, I marked it with the question marks because the Every of these 4 models is independent. They are not aware of each other. And this led to some serious issues. If we, for example, take a look at the first 3 examples, these are laser printers. And the last one is a laser level. So this is something completely different. Laser level is just to check how even things are, and laser printers are printers. So let's say that we send in this string, the laser level string, and let's say, OK, the first model will predict it correctly. It will say it's an equipment tool. But what happens if we have a mistake in the second model? What if the second model thinks, laser level, it contains the word laser, so I guess it's a laser printer. Because I've seen so many laser printers, this is probably a laser printer. And it will say, OK, it's category number 2. And now you see how can this lead to some really wrong paths. Basically, what happened here is that laser level will be mapped to a pressing tool, which is completely wrong. So now I got really worried, like, what should I do now? This was not working for me. And I Googled it. I found only a couple of scholarly articles on this topic, but no implementations. And then I decided to actually write my own solution. And this actually led to success. So let's say I introduced this hierarchical model structure. So what is the trick? We have some input, like laser printer. We tokenize it. We send it to some model. Now, of course, the obvious thing is that the first model, it predicts only the first level. It has only 24 output classes. It would be pretty confident. And then the trick is that we take this information and pass it down. Now, how do we pass it down? What I did is I actually trained separate models. I call them specialist models for every of these subclasses. So for example, for the second level, I trained 24 models. Now you would think, OK, what happens if I have 500 subclasses or 1,000? I think it's still not a challenge, because we are talking Python. The whole model code, the whole model data splitting is actually generated via script, so I don't find it really difficult. So actually what happens now is that, OK, the first model predict 19. It will say, OK, it's information and communication technology. And then I boot up the next model, which is only in charge of classifying the second levels of information and communication technology. And again, we have there 12 output classes, so again, it will be pretty much confident. And I continue this down to the 4th level. Now, in many cases, I noticed that it's enough that we predict the first level, the second level, and the last 4 numbers I could do even in one model in lots of the times. So this was the key. It showed some really great validation accuracy and testing accuracy. Just to show it once more together. So as I explained, we have an input string, and then we tokenize it, pass it to the first model, predicts, and then sends it down, boots up the next model, and this one also predicts the second level, and we continue this down. Just to compare this once more together, so if we have one model, the pro would be that it's easy to maintain. We have one model, right? But it has larger number of output classes. It showed really low accuracy, and it can lead to weight vanishing. And we just have one model, right? It's not really possible in most of the real cases that we resolve everything in one model. In the middle, you can see like the 4 models approach. So the divide and conquer. It's still easy to maintain. We have a bit more room to play around. We have 4 models, but unfortunately, it loses the hierarchy, and the accuracy was not satisfactory. And the hierarchical model structure has really high accuracy. It trains faster, because we can train the models in parallel. They are working only on the subset of the data that they are concerned with. And this is the most fun part. We can have different layer configurations. We can play around with keras. We can just wrap it around. And we can try out different hypotheses. The contra, they say it would be maintenance overhead, but I actually don't really see it because as I said, we are talking Python. It can be scripted. It can be done overnight. It's not a problem. So typical model configurations. I just wanted to highlight some typical models that I used. So on the left side, actually, you can see a model which was in charge of elements which contains typically just a few words, And actually, I borrowed the global averaging layer from convolutional networks. But it does actually, it pops out the most important word. And what this means is that in some cases, it's enough if we decide, OK, this is a paper, this is enough information, we will use that. But what happens if we have some complex scenarios like a luminaire for a number of houses? What is that? Like, is it a luminaire? Is it a number? Is it a house? What is it? And therefore, for these solutions, where we really depended on the context of the word, I actually used the GRU layer, which is a recurrent layer, and it learns really greatly the context of the words. I would just like to mention here, I didn't use any pre-trained embedding layers, like, I don't know, the glove or the word2vec. It was just simply not working for me. Why? Because our data is containing really lots of procurement-specific terms and product numbers and so on, which are not present on Wikipedia, right? So the pre-trained algorithm just couldn't figure it out, couldn't figure out the words. So actually, I trained my own embedding layer, and it is working fantastic. For example, if you would say, OK, give me the closest word to pencil, it would come up with something like marker. So it was really amazing to see how actually it learns. It's really good. Before I wrap up, I would like to mention one more thing. I call them the lines of defense. So we don't have to use AI all the time, right? We just have to use AI or machine learning for the complex tasks. But as it's implemented in my solution, if we have a term and we can do a direct lookup, this means that we don't have to use the ML because we just know, OK, this is belonging to that category, and we return the result. For typo detection as well, if we detect that there was a typo, then we again try to do a direct lookup. If there is a direct match, we just return it, and we are all set. Same things for the synonyms. As I mentioned, these 12,000 synonyms that I extracted, if we figure that the entered word is like synonym of another one, and if there's a direct lookup, then we return it. So yeah, we just use the machine learning on the end where it comes to really complex cases. Outcome. It is a classification service in production. It has a really high validation accuracy. The predictions are explainable, right? Because you can see exactly how it goes down through this hierarchy. It's easily adaptable. We can play around with the small specific networks, and we can just adjust them according to the needs, right? And it's really fast, like TensorFlow serving and Flask together. They're playing really well together. We integrate it into the process, and it just works flawlessly. And the benefits for our customers would be better spend segmentation, the initial problem that I mentioned, so therefore they have better insight into their spend, increased efficiency, and the most important thing, our customers now have a strategic advantage because they know, OK, we spent this and this much money on printers last year. This time we can get a better deal. I think we're living in exciting times. As you've seen, it's really easy to prototype a neural network. As far as I've seen from the previous talks, especially in the cloud area, we are not limited by processing power, so we can really leverage our creativity. Thank you.
Thank you, Emir.
I was on time.
We've got lots of time for questions, and there are questions as well.
All right.
So Slido will show us in a second. In a few seconds. We have, here we go. So let's have a look. So someone asks here, what if there are more than 4 levels?
I mean, I see your question. This would apply, for example, if you have some books or something like that. Then we would have to consider other solutions. What I stumbled upon and what I want to implement right now is the ragged tensors from TensorFlow. The cool thing about ragged tensors is that it actually captures the hierarchy, so we can actually pass that in right away from the beginning. So I think this would be one of the solutions for your question.
All right, thank you. The next question is this solution language agnostic?
Yes. Yes.
Simple.
Yes.
OK. Did you want to add more?
No, it's a simple answer.
The answer is yes. How large are the models?
Yeah. So they range. The biggest one is around 200-300 megabytes. And the smaller ones, of course, the specific ones are smaller. It also depends how many parameters you train. If you have an embedding layer which you train, of course, it will grow. If we'll have some simpler configuration, it will be smaller. So it's not possible to say just, OK, these are, they can fit into memory. It works fast. Yeah.
Right. Cool. So the next question says, how often do you still get wrong results? How do you find out that an item was misclassified, and how can you use that information to improve the system? So a multi-layered question here.
Yes. I guess what you mean by that is a feedback loop. Of course, we have a feedback loop, and we leverage this. We put in into the weight balancing, so it's a really good question. The wrong results, yeah. As I mentioned on the beginning, I take some portion of the data on the beginning, put it aside, and this was used for testing, of course. So for a large data set, it doesn't have to be this, 20%. It can be 1%, 2%, 3%. But because I have worked with 30 million articles, so it doesn't make sense to have a validation set of, I don't know, 30, 50,000 articles, I think. Yeah.
All right, thank you. Someone asks, how long does it take to retrain?
Yes. Obviously, the first one is the most time, because it works with the whole data set. 20 minutes. The smaller ones, in a couple of minutes. So they can be parallelized. It's really fast. And again, it depends on your hardware, right? So, yeah. OK.
So the next question here we have is, having faulty results, or just results or faulty results from 4-model configuration, why not do correlation with existing hierarchical catalog and correct the faulty level?
Yeah, I don't like to use correlation in that sense. So maybe we could discuss after, but I don't see it right now.
All right. And we've got one more here. So how large was the training set?
So 30 million articles minus the few percent that I use for testing. And this is how big it was.
OK. Thank you for all the questions. And thank you once more to our speaker.
Thank you.
Thank you, Emir. OK.